Hi everyone. So now we're going to do some examples of applying L'Hopital's rule when we are allowed to apply L'Hopital's rule. So the first example we're going to show is one where it looks like L'Hopital's rule applies, but it actually doesn't. So let's look at the limit as x goes to pi from the right-hand side of the sine of x over 1 minus the cosine of x. Now your first impulse, once you know L'Hopital's rule, is just to apply it every single time you see a limit that has a ratio in it. If you do that, you're going to get the wrong answer here. And the reason is that this ratio is not indeterminate. Remember, the first step when you're evaluating a limit is checking to make sure that the ratio you're working with is actually an indeterminate form. Where does the numerator go as x goes to pi? Well, the sine of pi is 0. So the top goes to 0. Don't leap ahead and think, oh, that's it, I can do it. Because what does the bottom do? Well, as x goes to pi, the cosine goes to -1. And 1 minus -1 is 2. And 0 over 2 is not indeterminate. In fact, this function is continuous at pi. And its value is equal to 0. So no L'Hopital's rule here. L'Hopital's rule only applies when the function is in an indeterminate form. It's possible that you might have to use L'Hopital's rule twice. So I could have a function that looks something like this. The limit as x goes to infinity of e to the x over x squared. Now before I even begin, I suspect that this limit is probably infinity. And the reason is that exponentials grow way faster than polynomials. And so the numerator of this function is growing to infinity like mad, and the denominator is growing to infinity, but not anywhere nearly as quickly. And so what that means is my suspicion is that this limit is infinity. But I can't say it without some sort of mathematical justification. So what I'm going to do is I'm going to use L'Hopital's rule. The top, if I'm allowed to use L'Hopital's rule, the top goes to infinity. The bottom goes to infinity. So this is an infinity over infinity form, and I am allowed to use L'Hopital's rule. Well, the derivative of e to the x is e to the x. And the derivative of x squared is 2x. So what I've used here is d by dx of e to the x is e to the x. And d by dx of x squared is equal to 2x. So I'm replacing the original ratio with this ratio that I built out of the derivatives. The problem is this is also indeterminate because this goes to infinity and this still goes to infinity. Well, in this case, I could actually apply L'Hopital's rule again usefully, because what's going to happen is the denominator will stop tending to infinity. Here I'm going to get the limit as x goes to infinity of e to the x over 2, because d by dx of e to the x is e to the x, and d by dx of 2x is just 2. Well, I can plug in again. Where does e to the x go as x goes to infinity? It tends to infinity. Where does 2 go as x tends to infinity? It goes to 2. And infinity over 2 is infinity. Okay, so it's possible that we can have another indeterminate form that I didn't cover in the notes because it's harder to work with, but it's still something that might show up in the exercises. And that is when you have something that looks like infinity minus infinity. So we have a function that's running off to infinity, subtract with another function that's running off to infinity. That's also indeterminate because you don't know what the balance of growth is between those two functions. As an example, let's consider the limit as x goes to pi over 2 from the left-hand side of the secant of x minus the tangent of x. Now the secant is equal to 1 over the cosine. In fact, if you draw a graph of the secant, why is this even an interesting question? Well, what's happening here at pi over 2 is that the cosine looks like this. And that means the secant looks like this, because remember, the secant is just the reciprocal of the cosine. So secant is tending to infinity. Well, what's tangent doing? Tangent comes in like this, and it also goes to infinity. So secant is tending to infinity as we come into pi over 2 from the left-hand side, and tangent is also tending to infinity as we come into pi over 2 from the left-hand side. So if I subtract them, do I get a number, or do I get 0, or do I get infinity? So this is what's called an infinity minus infinity form. So here the strategy tends to be, I can't use L'Hopital's rule unless I have a ratio, so I should build one. And that means I'm going to rationalize this, which means I'm going to put it over a common denominator and see what happens. So this is equal to the limit as x goes to pi over 2 from the left-hand side of 1 over the cosine of x minus the sine of x over the cosine of x. And that's equal to the limit as x goes to pi over 2 from the left-hand side of 1 minus the sine of x over the cosine of x. Now, I've got a ratio now. I should probably check to make sure I can use L'Hopital's rule on it. Well, as x goes to pi over 2, sine goes to 1. So this tends to 1, which means the entire thing tends to 0. As x goes to pi over 2, cosine goes to 0. So this is a 0 over 0 indeterminate form, and I am allowed to use L'Hopital's rule. That gives me that this is the limit as x goes to pi over 2 from the left-hand side of the derivative of 1 over sine, which is minus the cosine, over the derivative of the cosine, which is minus the sine. The cosine of pi over 2 is 0. The sine of pi over 2 is 1, and so this limit is 0. As our final example, let's do something in the power form. So suppose I wanted to know what the limit as x goes to 0 of x to the square root of x is. So this is going to be of the form 0 to the 0, which is indeterminate, but not an indeterminate form that I could use L'Hopital's rule on because I need a ratio. So I'm going to use the e log trick. This is equal to e to the limit as x goes to 0 of the square root of x times the natural log of x. And the reason that's true is because e to the natural log of x to the square root of x is equal to e to the square root of x times the natural log of x. I still can't use L'Hopital's rule here because this is a 0 times infinity indeterminate form. So I'm going to have to use the ratio trick and use reciprocals to write this as e to the limit as x goes to 0 of the natural log of x divided by 1 over x to the 1/2. Now if I take derivatives of top and bottom, which I'm justified in doing because this tends to minus infinity and this tends to positive infinity, so I can use L'Hopital's rule. The derivative of the natural log of x is 1 over x. And the derivative of 1 over x to the 1/2 is minus 1/2 over x to the 3/2. And if I do some algebra on that, what I'm going to end up with is e to the limit as x goes to 0. You invert the fraction, you multiply by through. What you're going to get is minus 2x to the 1/2. And that limit is continuous at 0, which means you get e to the 0, which is 1. Okay, so those are the basic forms that we have to know when working with L'Hopital's rule. There's a lot of examples in the chapter as well. You should consult those if you see a homework exercise that doesn't look like one of the ones I've covered here. But these require practice, so please do as many as you feel comfortable doing. And then do some more, because why not? All right, I'll see you next time.